Okay, I'm here today to tell you a bit about the Australian desalination program. As you probably have read in the newspapers, we've been very active in desalination since about 2003, when the plans started for the first desalination plant. We have 6 plants, very large, that deliver water to the municipalities in and around Australia. They all use reverse osmosis. They all use green energy offsets, 5 of them directly from wind farms into the grid and out, and the other uses renewable energy credits. So we're trying to be very green as much as possible in Australia. They all use media or membrane pretreatment, so nothing out of the ordinary. This is technology that's used around the world. Run you quickly through them. The first one to be built that started this whole thing was the Perth Seawater Desalination Plant. They started planning in 2003. They let the contracts for building in 2004 and drew first water in 2006. Rather remarkable. And this was a plant that was shoehorned into 16 acres that were available on an industrial property. One thing to remember is, in this case, and I've put these in red so it'll show up on each of these slides here, it's 38 million gallons a day, and wind power is used as an offset. The next one is the Gold Coast Desalination Plant. This was built in combination with what was called the Western Corridor Project, which took wastewater, repurified it, and then built pipelines to deliver the wastewater to where it was needed and desalination water where it was needed. So it was a very unique project and good thinking on the part of the people in the Gold Coast. It is also 38 million gallons per day, and this one uses the renewable energy credits. This is the Sydney Desalination Plant, 66 million gallons a day, and it's been built so that you can double that size if you ever needed it. It uses wind power as an offset. The Victorian Desalination Plant, probably the most expensive that was built in Australia. As you can see, the roof is green. They've gone to great lengths to make this environmentally acceptable to the public. And in fact, if you look closely, you can see a berm that's been built around the plant, so you cannot see the plant from the nearby road. So they've gone to great lengths and cost a great deal of money. It's 120 million gallons, or Tom corrected me this morning, but about 110 million gallons a day. But nonetheless, a very large plant, and they use wind power as an offset. Having trouble here. This is the Southern Seawater Desalination Plant. It's the second plant that's being built in Perth. When this plant is completed, the 2 plants will produce more than 50% of the total water demand for the city of Perth. This was after the first section was completed, and if you look at this area over to the right, the second section has now been constructed and is being commissioned. So they do things rather quickly in Australia once they make their mind up, and I'm proud to say that it's been fun working with them. This was the Adelaide plant that I skipped over the first time. It's 72 MGD. So each of these plants, as you can tell, is very good size. They use wind power as an offset. So to give you an idea, the Brisbane, Perth, and Adelaide plants will eventually produce 50% or more of the water for that particular city. In Brisbane, it also includes that Western Corridor because they are using membranes for the wastewater treatment. Melbourne just built, maybe around 20% or plus minus, and Sydney a little bit less. Of course, Sydney is the biggest city in Australia. The sad thing about this at the moment and I must say this because it's a fact, 4 of the large plants located on the East Coast are currently shut down. All the reservoirs are full, or nearly full, so they shut the plants down. 3 of them are on what we call hot standby, where there's always some water running through. The other is going to a cold shutdown, and in fact they've capped the intake already. So I don't think it'll be very long, however, before they're going to need water again. The Sydney Reservoir is down to about 90% of capacity in 1 year, and it's evaporating at a rate of about 0.2% per week. So a couple of hot spells, which Australia happens to get, is going to increase that evaporation rate, and they'll probably have to start before they know it. Now to our center. Because of this building of desalination plants in Australia, the national government found fit to fund the National Center of Excellence in Desalination in 2009. They gave us $20 million in funding over a 5-year period, and the Western Australian government added another $3 million. And as a result of that, we developed a research roadmap, very similar to what Kevin Price and his group did a few years ago for the United States, and you know, that set the plan for all of our research in Australia. The Murdoch University, which hosts us, also gave us a 2-story engineering building that you see there, and the right-hand 25% of it we converted into a high bay pilot plant testing area. We also added a tank farm, drilled 3 wells actually, 1 well into the superficial aquifer, essentially drinking water, then went down further and tapped into an ocean reservoir, ocean aquifer. We're only about less than 2 kilometers from the ocean, and we get water of about 26,000 milligrams per liter. So we can mix and match those using all these hydraulics around the tank farm. The 3rd well was a surprise. They allowed us to drill a 3rd well where we can re-inject water that's been tested in the pilot plant area. It's a big surprise, really, as long as we don't add chemicals that are going to be toxic and so on. But nonetheless, we can take the permeate, for example, from a reverse osmosis system, and the concentrate, mix them back together and put them down into the aquifer, which is below where we are drawing water. So we have a very unique but interesting situation. This is one of the pilot plants. This happens to be membrane distillation that we're testing, and we have 8 different areas in this pilot plant facility where we can test small pilot plants, and we have area outside of the building where we can bring in trailers or much larger plants. We have 14 research partners, 13 are universities, and 1 is CSIRO, the Commonwealth Scientific and Industrial Research Organization. Each of those partners is a stakeholder, and they contribute $100,000 a year, which covers the overhead for running our center. This looks funny. This is really the Earth, and it is really round. But some of these slides were actually prepared for widescreen, and I wasn't smart enough to know how to take care of that problem. At any rate, in Australia, we are using all of our universities. In addition to the stakeholders, we've employed a collaborative approach. I've insisted that in order to make these research projects more robust, you have to have good collaboration. So, like it or not, I have forced the East Coast universities to collaborate with the West Coast universities, even though we know we're more than 5 hours apart by airplane. And that is a long distance. Having traveled it many times, I realize that there's a resistance to doing that. But they've bought into it, and we've also have some other research centers, water utilities that are partners, the mining industry, government, and of course some of the private industry people. Around the world, I've called on colleagues around the world that I've been able to develop over the years, and a good number of years, and I've been very fortunate. So we have collaborators from the USA, Asia, Europe, and the Middle East. We have over 90 national and international research partners. This effort was started 2.5 years ago, so we're now into our 3rd year. So we've got quite a bit moving in that period of time. We have more than 30 international collaborators, and you'll recognize University of Texas El Paso. They're helping us with one of our concentrate minimization projects. So we're thankful for that. And some of these others you recognize. Nanyang University from Singapore, Kaustin is from Saudi Arabia, UC Irvine, and some others. So we've been very fortunate in involving these people in this research. Now, I realize that this may be a little bit small, but we have 272 research people now working on our projects. 34% are getting their doctorate or are postdocs. We have 17% that are professors, other students 10%, associate professors 12%, and others, mainly collaborators, 25%. So a pretty good mix of research scientists. And the reason, of course, I'm here is to talk to you about some of those research projects. We have 44 research projects at the moment, and we are not done yet. We've had 4 funding rounds. We've invested over $11 million of our government funds, and including cash from partners, industry partners, and in-kind contributions from the universities, it totals about $38.5 million. I think that's fairly good leverage. So we're proud of that. Proud that we've been able to do it that way. It's much easier to go out and seek money when you go with money, and that's a lesson I learned from Ron Linsky at National Water Research Institute a few years ago. So we have a very robust program. Now, we have 5 areas that we have a mission to address. Pretreatment for desalination plants, reverse osmosis in general, novel desalination plants, concentrate minimization, and the social sciences. Now, 13 of those are involved with reverse osmosis. We have the big 6. They still have some challenges. We're trying to address some of those challenges to make the plants more efficient, more cost effective. 8 projects on pretreatment, 6 on novel technologies. And yes, we do have some novel technologies that we're looking at. 9 of these projects, you'll notice, are on concentrate minimization. So we think it's very important. The big plants have been built on either coast, and there may be a few more very large plants built, but we feel that it's very important to pay attention to inland and remote communities. So much of our effort is looking at what do we do with the concentrate. You can't put in a desalination plant without that concentrate. And 8 projects are directed toward the social sciences, things like public perception, how does the method of project delivery affect risk liability and cost of plant, etc., and trying to put it in a form that the general public will appreciate. Some of these research projects have to do with our own concentrate minimization, submerged hollow fiber membrane distillation with transverse mechanical shear. That's a long, very technical titled subject, but very simply, it's a way of taking a stream that is very near saturation, allowing it to crystallize as you draw water out of this saturated solution, and you then vibrate it transversely in order to knock the crystals down to the bottom and then put it into a reactor and separate. So it's working extremely well. They're in their first year, but the results have already been very promising. Minimizing RO brine with membrane distillation and crystallizing it. The interesting thing about membrane distillation and you'll see that in several of the projects, is that we can take reverse osmosis concentrate and concentrate that, minimize that volume considerably using membrane distillation. University of Queensland has a high recovery ceramic membrane that they're looking at for high recovery and membrane distillation. At Curtin, they're looking at an old technology, rather old technology, vibratory shear membrane technology to raise the recovery. But all of these, of course, are to minimize volume. University of Wollongong is addressing a very real problem and probably can be related here to the U.S. as well. And it has to do with extraction of water and minerals from coal seam gas produced water to reduce the volume. It's a very real problem, and I know that in the U.S. there's quite a bit of controversy now about fracking, and some of the things that we learned there may help with that problem as well. We have been able to already get up to about 95% recovery, and we may be able to take it even higher. At Victoria University, looking strictly at things like silica removal, and that's where the University of Texas El Paso is sharing their knowledge with us. At University of Technology in Sydney, we have an interesting process that is called fertigation, and that's using liquid fertilizer on one side of a forward osmosis membrane and taking a saline solution, or the more dilute solution on the other side, and drawing water out of brackish groundwater. It dilutes the fertilizer, and up till now, we've had to separate the draw solution from the water, but in this case, the liquid fertilizer can be used for crop irrigation. So we've eliminated that one problem with the FO process. And it solves a problem that's very unique to Australia, and it's called salinization. As the groundwater rises in the basin, the Murray River has been getting salinized, higher in salinity. And how do you stop that? Well, the quickest way they could do it was to drill a number of wells and pump water out, and that reduced the hydraulic gradient, and therefore the Murray River continues to be the source of water for Australia's breadbasket. But that's not a very sustainable process, and there are more than 15 of these what they call salt interception schemes. So the scientists at UTS looked at using fertilizer-driven forward osmosis as a way to reduce that volume. That doesn't totally answer the problem, but it does reduce the volume considerably, and then we'll go the rest of the way some other way. Very quickly, the saline water that's pumped out of the ground goes on one side of the FO membrane here. Fertilizer solution is prepared. The concentrated fertilizer then is pumped on the other side of the FO membrane. By forward osmosis, water is drawn out of the saline water. The diluted fertilizer then is adjusted in concentration to whatever is desired and then sent to the fertigation system. The rest of the fertilizer is then reused back within the system. So a very clever way of using forward osmosis. Let's look at a couple of the so-called green energy research projects that we have. We're using CDI, which is a new technology, capacitive deionization technology, and we've involved a good number of partners on this particular project. We have two projects running in parallel. One that is looking at graphene to produce the electrodes to increase the capacity of the membrane of the electrode to absorb ions, and the other is to take a mobile pilot plant using a commercially available CDI plant to see what kind of problems we're going to run into in a remote plant. The area we chose was just a little bit out of Alice Springs. So if you've ever known where Ayers Rock is, it's not too far from there, and it's south of the greenish part of the Northern Territory, but it's out there in the middle of nowhere, very hot. Capacitive deionization, most of you are familiar with, but we use an electrode that's can be charged. We use positive and negative. As the saline water comes through, the ions are adsorbed onto the electrode, the positive to the negative electrode, and the negative to the positive electrode, until the electrodes have been fully have been filled. All the sites have been filled, and then you desorb it by removing the charge. The ions then are released from the stream, and they're expelled from the system. So at the moment it's it's not a continuous process, but if you can imagine a number of these working systematically, you can see how you could develop a continuous system. What we're looking at is graphene flakes. Graphene nanoflakes have a much greater capacity to absorb ions. They're much greater than even activated carbon. Activated carbon is the current material of choice, but we think this is going to improve the efficiency considerably. This is the pilot plant that we did send out into the outback. Worked very, very well, 30 consecutive days, so we know it's going to function. We did just outfit it with some photovoltaic cells, and we're going to then power it with these cells. Of course, all of you that have worked with energy know that the converter to go from PV to direct current to an alternating current consumes a good deal of energy. So we think this way is going to be much more efficient. Our hope is that we can build a small stack using the graphene electrodes and replace the commercial stack that is in this pilot plant at the moment, and then take the whole assembly out into the field. So that's the target. We have a membrane distiller that we are designing for use at a remote community in the Great Victoria Desert in Western Australia. Uses membrane distillation, and this just describes what membrane distillation does. Most of you know about it, but very briefly, you add some heat to the water, and we're going to use solar collectors to do that. And then as you heat up water, you can actually cause the water to evaporate. The vapor goes through the membrane, but the membrane is hydrophobic, so the water stays behind, very similar to Gore-Tex type materials. And in fact, PTFE is one of the membranes that are used for this particular process. And then the vapor is condensed on the other side. And then this is, in the process we're using, this goes in series through 4 different stages to give us a little bit higher recovery through one pack. The industrial, well, I've skipped through the next slide. This is where we're going to put this plant. This is Junjara. It's out in the middle of the desert. It's green in this photograph because this was right after probably the only spring rain they had. So everything was green, just like California before summer comes, Everything is green, and then all of a sudden it turns brown. But at any rate, this is about 1,300 to 1,500 kilometers northeast of Perth. So it's a long way from anywhere. It's totally off the grid. They do have some diesel gen sets right now, but that's a temporary measure. And we hope to put this plant there. Now, we're using a fairly new solar collector. That is an interesting one. It produces both photovoltaic energy, direct current, so we can use that for the pumps And there is a small vacuum pump that we use to increase the flow, vapor flow. And it's all packaged together, made in here in California. But it's an interesting one. I think others will be taking a look at it. We have a lot of industrial waste heat. Contrary to a lot of opinion, there is a lot of waste heat in the industry, particularly from the mining industry. So we're using a new novel multi-effect distillation process. In addition, we're looking at geothermal energy to drive this low-pressure process. This novel technology, MED technology, was developed at University of Western Australia, and the industry partner on this is an alumina refinery in Western Australia. So it's going to use waste heat. It appears that it'll improve the MED efficiency by about 30%. This is the pilot plant, small pilot plant that we have built for testing at Rockingham, our test facility, and from there it'll go on to the refinery. We are looking at the geothermal energy. This happens to be a site where they're drilling a well. Other projects that may be of interest to you, and I bring these up because there's probably not enough time to go through all of these. There are desal opportunities in Australia for agriculture. Hard to believe, but there are. And I'll give you an example if I have the time. We're looking at public perception of desalination, particularly right now in the Victorian region, the Victorian state, where the opposition to desalination has grown substantially due to the recent floods. We're looking at project delivery methodologies, the biofouling control for the big plants, prevention of additives to prevent or control membrane surface modification, and on and on. We're looking at hot standby management for these plants that have been shut down in hot standby. How do you do it properly? How do you do it safely? How do you restart them? Environmental impacts, obvious one is, the brine from a desalination plant. How do you put it back in the water without affecting the environment around and the fauna? So even though those have been looked at many times in the U.S., we have to do it once again in Australia. We're looking at smart materials for corrosion control, and the list goes on. Now, this is Sundrop Farms. Very quickly, they take seawater, convert it to fresh water. They're coming from the Spencer Gulf, very much like some of the water in the Arabian Gulf, very shallow Gulf. Surprisingly, 57,000 milligrams per liter. They use a parabolic solar collector and MED. These are the collectors, and they're growing tomatoes. They're marketing them, doing extremely well because they can control the size and color and a lot of things that you can do under a roof. We have a lot of international collaboration. I look much thinner there, don't I? That's pretty good. I like that. We do a lot of collaborating with KAUST in Saudi Arabia, with the Megaton project in Japan, the Singapore Membrane Technology Center, and Korea. So that I think it makes for much more robust projects when you have these kind of people participating. We participate in international congresses. We have international workshops. We have a discovery center for the kids. We have a 3D multimedia room where we have developed a video that's in 3D to help people understand what we're doing. And with that, I thank you very much. I wish I had more time because I have a lot more that I could be talking to you about, but as you can see, we've built a very robust program, and I think touching enough of the areas of desalination that and which many can be used not only in the U.S. but particularly here in Texas.
Well, thank you for that, Dave. And I want to remind everybody that we will have time for questions from the audience after all the speakers finish. And for the people on the webcast, they are welcome to send their questions in. But Dave, I just wanted to ask one quick one here, and that is, you started off by talking about the big seawater plants. And the seawater plants, by virtue of their size and complexity, they usually get all the press. But I noticed most of your research looks like it's focused on brackish water stuff. Is that? Could you speak a little bit about the importance of brackish water to Australia?
I focused that for this talk today because I know brackish water is of great concern here in Texas. So there was much of my talk on the brackish water end of it. But if you dissect the particular projects we've got, those in RO, those in the concentrate issues and environmental, social impact, those are related to the big desalination plants on both coasts.
Okay, good. Thank you, Dave.